Hello everybody, my name is Davide Coraci, I am a research fellow from Politecnico di Torino and a member of Beta Lab Group. Today, I will present a paper developed with my co-author here listed, entitled Energy Management of a Residential Heating System through Deep Reinforcement Learning. This work aims to show how artificial intelligence could be combined with energy management to enhance energy efficiency and comfort in buildings. Nowadays, buildings are becoming more and more complex due to the increased penetration of multi-sources HVAC systems and the increase of distributed renewable sources and storage. This increased the energy flexibility, but at the same time requires innovative solutions for the optimal management of energy systems in buildings. The energy flexibility represents a fundamental characteristic of a smart building and defines their ability to adapt and respond to grid requirements, climatic conditions, and user needs. Classic control strategies such as on-off and PID, are mainly reactive and unable to predict changes in weather or building conditions, and their implementation results in suboptimal control policies. To overcome such limitation, the application of adaptive control strategies has been explored in the last few years. In particular, model-based control strategies, such as model predictive control, were explored to overcome such limitation, showing an excellent ability in improving comfort conditions and energy efficiency in buildings. However, a significant problem in model predictive control is related to the performance dependency on the model definition for the control strategies optimization, which is often challenging to design with good accuracy. As a result, the interest in model-free control strategies has increased since it does not require prior knowledge of the process or environment to be controlled. Therefore, in this paper, it was designed an adaptive and model-free strategy based on deep reinforcement learning to manage the supply heating power per each floor of a residential building for enhancing energy efficiency and indoor temperature conditions. The occupant building interaction was considered as part of the control problem using a probabilistic model which simulates the opening and closing of windows. Firstly, a sensitivity analysis is carried out on the hyperparameters of the model to assess their impact on the performance achieved by the control agent during the training phase. Then, the best configuration is adopted for testing the adaptive skills of the controller by changing some forcing variable consisting of 4 different control scenarios. Reinforcement learning is an area of machine learning, often using control theory in which an agent learns an optimal control policy that maximizes an objective function through a trial and error interaction with the environment. The controller, called agent, is connected to an energy system and selects a particular action to maximize or minimize an objective function named the reward function. After performing some action, the environment provides the agent the corresponding reward and information about the new states, for example outdoor or indoor temperature. Then the agent analyzes the new information and provides new actions. Mathematically speaking, the problem can be defined by 2 functions, namely the state value and the action value function, that are used to quantify the goodness of a policy. The combination between deep neural network and reinforcement learning algorithm seems to overcome computational problems related to complex state space representation, leading to what is called deep reinforcement learning. In particular, in this paper, it was implemented the soft actor critic, an off-policy algorithm capable of handling continuous action space. This method adopts an actor-critic architecture that employs 2 different deep neural networks, the actor and the critic, that approximate respectively the state value and action value function. Moreover, the entropy regularization represents a key feature in soft actor critic, ensuring that the agent is pushed towards the exploration of new policy, while avoiding that it gets stuck in suboptimal behavior. The proposed control strategy was developed for a 5-story residential building located in Turin. The building is organized into 5 different thermal zones, 1 per each floor. The thermal zones are served by a radiant floor heating system equipped with a natural gas-fired boiler and variable speed circulation pump. 4 different probabilistic models that simulate the occupant interaction with the building concerning the window opening or closing were implemented and tested within the simulation environment. These models are based on the logistic regression and propose 2 equations to predict respectively the window opening or closing. After a qualitative analysis, the model proposed by Anderson was implemented in this case study, and this model employs indoor temperature, relative humidity, and carbon dioxide concentration, along with outdoor air temperature, wind speed, and solar radiation, to estimate the probability of opening and closing of windows in the building, and the coefficient of logistic regression depends on the day of the week and the time of the day. Here is presented the methodological framework with the aim of introducing each stage of deep reinforcement learning controller development. The interaction between the controller and building energy model was simulated through building control virtual testbed that allows the information exchange between the building model developed in Energy Plus and the reinforcement learning controller developed in Python. The first stage of the framework was aimed at defining the main components of the reinforcement learning control problem. The action space includes all the possible control actions that can be taken by the controller. The reward is a function which describes the performance of the control agent with respect to the control objective. Finally, the state space is a set of variables related to the controlled environment which are fed to the agent in order to learn the optimal control policy which maximizes the reward function. In the second stage of the process, the deep reinforcement learning agent was trained. Reinforcement learning agents are characterized by many hyperparameters which require appropriate tuning. Therefore, in this stage, a sensitivity analysis was carried out on some of the most important hyperparameters by training the agent with different configurations, in order to analyze the variation in the result obtained and to identify the best solution with respect to the metric adopted. In conclusion, the best trained agent was tested during the deployment phase in one episode which includes a different period from the training episode. Moreover, the deployment was performed in different scenarios, including different indoor temperature requirements and building envelope properties from the training stage, comparing the performance of baseline and reinforcement learning-based agents. The performance of deep reinforcement learning controller was evaluated against a baseline controller consisting of a combination of rule-based and climatic-based logics for the control of the supply heating power. The rule-based controller managed the operation of the radiant heating system according to the indoor temperature values and the occupancy schedule separately per each floor. The heating energy to each floor is applied 2 hours before the arrival of the occupants or when the indoor temperature is lower than the lower threshold of the stability range during the occupancy period. Contrarily, during the unoccupied hours, or when the indoor temperature is higher than the upper threshold of the stability range during the occupancy period, the heating energy is not supplied. The controller is to maintain the indoor temperature into an acceptability range defined between -1 and 1 from the desired temperature value of 20 Celsius degree, while reducing the heating energy provided to the building through the regulation of the heating power supply to each radiant floor. Since soft factor critic was selected as the control algorithm, the action space was expressed as a continuous space of 5 different actions related to the supply power per each thermal zone, defined between 0 and the effective nominal value and expressed in kilowatt. The state space is composed of 26 observed variables. The variables chosen are feasible to be collected in a real-world implementation and provide the necessary information required by the agent to predict the immediate future rewards. The reward function was formulated as a linear combination of two different parts, an energy-related and a temperature-related term. They were combined and employed two weights, delta and beta respectively, that were made to vary in order to change their importance. The energy term refers to the heating energy consumption calculated in kilowatt-hour and tries to minimize this value. The temperature term was evaluated as the temperature difference between the upper or the lower threshold temperature of the stability range and the indoor air temperature, with the aim to maintain the desired indoor temperature conditions. The reinforcement learning framework is characterized by a number of hyperparameters that strongly affect the behavior of the control agent. In order to analyze their impact on the performance of the controller, different configurations of the most interesting hyperparameters were tested and compared in this study. To assess the goodness of the deep reinforcement learning controller configurations, suitable key performance indicators were introduced. In detail, two metrics were selected during the 2-month period of operation and summed up at the end of each training episode. The energy saving, considering the amount of energy supplied to each zone with respect to the baseline, and the cumulative sum of temperature violation during the occupancy hours. A temperature violation occurred when, during the occupancy period, the temperature was not within the acceptability range -1 of the 20 Celsius degree set point. It was calculated as the absolute difference between the indoor temperature value and the lower or upper limit of the stability range, when the internal temperature was lower or higher than these limits. Moreover, these metrics were also calculated for the baseline to compare its performance with the deep reinforcement learning agent. The best configuration of hyperparameter retrieved from the sensitivity analysis performed during the training phase was chosen for testing the adaptability of the agent in 4 different scenarios during a simulation period that includes January and February. The scenarios considered include variation of outdoor conditions, changing the simulation period with respect to the training phase, increasing of the temperature set point, changing the indoor temperature requirements and the acceptability range, and variation of building features, wind thermal transmittance and solar gain coefficient and internal mass, improving the performance of the transparent building envelope and the thermal inertia of the building. The results of the analysis are presented at 3 different levels, starting from the training phase up to deployment phase results. The results obtained for 15 agent configurations were compared in the sensitivity analysis performed during the training phase in the last episode. In particular, it was compared the performance of rule-based controller and different configurations of deep reinforcement learning controller, showing in a 4-quadrant visualization the cumulative sum of temperature violations during the occupancy period, in logarithmic scale for the sake of clarity, as a function of the heating energy saving with respect to the baseline. The black dashed lines indicate the performance achieved by the baseline controller. The left bottom quadrant includes all the solutions that they performed better than the baseline both in terms of temperature control and energy consumption, and worst solution corresponding to higher energy consumption and temperature violation than the baseline should be displayed in the right top quadrant. At the end of the sensibility analysis, results that the configuration 8, whose hyperparameter as specified in table, guarantees the best trade-off between energy savings around -5% and temperature violation around -65%. The adaptability of the selected controller was tested in the 4 deployment scenarios, comparing the results obtained in terms of energy savings and reduction of cumulative sum of temperature violation with respect to the baseline. In all scenarios, the deep reinforcement learning controller leads to a reduction of heating energy supplied and temperature violations. In particular, the developed controller achieves the highest energy savings, around 5% in the 4th scenario, without reducing the temperature violation with respect to the baseline. In contrast, in the 3rd scenario, the deep reinforcement learning controller shows the highest reduction of temperature violation, around 60%, with the lowest energy savings with respect to the baseline, around 2%. A detailed comparison of the temperature trends observed for rule-based reinforcement learning controller during the 1st scenario provides further insight. In particular, the figures show the indoor temperature and supply power patterns for the ground floor. The adaptive controller is capable to reduce the temperature violation and energy supply through an optimal management of the heating system. The developed controller optimizes the preheating phase since it switches on the heating system later than the baseline, reducing the corresponding energy supplied and ensuring that indoor comfort requirements are met. In conclusion, the present paper clearly shows the possible improvement given by the introduction in residential buildings of adaptive and model-free control strategies for enhancing energy efficiency and comfort in buildings. Furthermore, the agent was found flexible and effective in adapting to modification in the controlled system, such as weather conditions, indoor temperature requirements, and building envelope characteristics. And now, which remains to be done? In the near future, we will be focused on the comparison between the developed soft actor critic controller and a model-based solution, such as model predictive control. A robust comparison between these 2 techniques in terms of control performance, computational cost, and modeling effort could provide useful insights on the strength and weakness of deep reinforcement learning controllers. Moreover, the evaluation of indoor thermal comfort could be performed by introducing parameters such as predicted percentage of dissatisfied and predicted mean vote in the reward function. Even if the monitoring of many comfort parameters is a non-trivial task in real-world application, in a simulative context, the evaluation of thermal comfort performance achieved by deep reinforcement learning agents could be explored. If you are interested to the topic, check out our lab website, or if you want more detailed information about our paper, feel free to write us an email. Thank you for the attention.